All right, we're going to move on. So we're going to get into vector fields again. We need to establish a few things first. An oriented surface is a two-sided surface. And then I put in there just for fun, there are examples of one-sided surfaces. A surface with one side. Anyone ever heard of a surface with one side? Yeah? What is it?
Mobius strip.
A Mobius strip. We'll do a quick example. There we go. So this is a surface with two sides, right? And we're not going to argue that the edge here is a side, and this is. You could argue that there are what, like 6 sides to this? But let's just say one side, two side. Yes. So if you take this and you twist one end, keep the other one fixed, twist it, and then paste this together like this, you get what's called a Mobius strip. And if you look at this and look at my index finger and my thumb, they appear to be on two different sides of this. But if you follow the paper around, you'll come around back to your thumb, and then you keep going, and you'll come back to your index finger, and then you'll be back to your thumb. So my thumb and my index finger are on the same side of this. So it's a one-sided surface. Kind of interesting.
I feel like that's out there. You can't say that. How can you say that?
That's an example right there.
Obviously two-sided.
I think I would have to ask you to prove to me it's two sides. You won't be able to distinguish the two sides from each other. Yeah. There's an even more advanced problem where what you do is you take that same idea, right? Well, let me try this first. Imagine this sheet was kind of like stretchy. Okay, so what would happen if I take this side and paste it to this side, right? That would be a two-sided surface still, right? And what happens if I take this edge, this circle, and I stretch this thing around to this circle, and I make this circle be like the same as this circle? Stretch it around like that. Then what would I get? A donut, right? We call that a torus. Okay, so let me back this up. What would happen if I go twist this and put them together? I get this Mobius strip, right? But at the same time I do that, I got to back this up. Sorry, I'm going a little far away from class right now. Call this side A, B, C, and D. So when I do the torus, what I'm doing is A and C are becoming the same point. B and D are becoming the same points, right? And then I'm letting this edge go get wrapped around to this edge. Yes, that's your donut. When I do a torus, I switch these, right? So A is going to go to D, and B is going to go to C. I want to do that, but at the same time, I want this edge and this edge to go to each other. Now, I can't do it, okay? I can't do it. But if you could, you'd get what's called a Klein bottle. And a Klein bottle is a four-dimensional object, and it's an example of a volumeless container. It's a solid with no volume. Just like the Mobius strip is a surface with one side, it's a volumeless container. It's weird. This is all studied in a class called, if you're interested, if you ever have the opportunity, topology. Not topography, but topology. Usually you wouldn't see that unless you're a math major. But interesting stuff. I spent like a year studying the difference between a coffee cup and a donut. And at the end of it, there's really nothing. There's no difference, okay? But it begs the question, I mean, like, what is the difference between a coffee cup and a donut? I mean, we obviously you can eat one of them, right? You can eat one, I mean, there's all these differences that we can say physical descriptions, right? But mathematically, what's the difference? And so the question is, what do you mean by mathematically, right? And really what it comes down to is that they both, here's a donut, 3-dimensional, that's not a very good donut. There's my donut, okay, you get it? And then here's my coffee cup. There's my coffee cup with my little handle on the edge. These are mathematically the same objects. There's no difference between the two. And the reason is if I draw arbitrary curves on this donut, that curve, I can shrink it down to one point without cutting through any part of the donut, right? That curve right there on the outside. But if I draw a curve that goes into the donut, comes back around the outside and goes like this, I can't shrink that down to one point without cutting the actual donut. And the same exact thing happens on here. I can draw curves out here that I can shrink down. I can even draw curves on the handle that I can shrink down. But there are some curves that I can draw around this handle, and then there's even the one around the cup itself, right? Which I cannot do it. So it's kind of like the piece of paper. You can deform it. You could deform a donut, or probably the other way around. You could, well, I don't know what makes more sense to you. I could turn this into this if I was allowed to deform them without cutting it or tearing it. Or I could deform this back into this if I'm allowed to, like, move things around. So they're mathematically equivalent. That's what topology gets into. I mean, in layman's terms. Coffee cup and donut. Yes, yes. All right, oriented surfaces. See how that little, I should just take that out of my notes. That just wasted 5 minutes. An oriented surface is a two-sided surface in which the normal vector at every point on the surface exists, and such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations. So I think if you just look at this, there's a sphere, right? There's a sphere. We know that at every point on the sphere, there's a tangent plane, right? We did that last class. We have tangent planes at every point. If you have a tangent plane, you have two vectors. If you cross them, you get a normal, right? So at every point, there is a normal vector pointing off of this surface. As you move around the surface, those may change direction. They may get shorter, longer, but they vary continuously, which means they don't automatically, like, all of a sudden go from here and then you move here and boom, and all of a sudden it's pointing inside. So that's what they mean by vary continuously. So we can look at all the normals pointing outward, which would be called positive orientation, or we could look at all the normals pointing inward. That would be negative orientation. But we can orient the surface, and any surface that we can do that on is called an oriented surface. All right? There are examples of surfaces which I won't get into that are not, you can't orient them. So how do we compute the normal vector of an oriented surface? Well, we've done this before. If the surface is given by a vector function, right? Then if we did the cross product of the partials, we did that on the sphere, cross product of those partials gave us a vector pointing out, which is what we use to find the equation of the plane. If we then divide that by its own length, it's a unit normal vector, isn't it? Yeah? If you take the negative of this vector, it's just going to point in the opposite direction. Okay? When your surface can be written as a function of two variables, x and y, so this is like a special case now, this cross product becomes this, and then the magnitude is this. So that should look familiar. This should look familiar to you. That's that was that shortcut formula we used a second ago? Square root of 1 plus partial of g with respect to x, partial of g with respect to y. Okay, but this right here, you would have to actually do the cross product to get that. With all that said, we now want to talk about a closed-oriented surface. So if the surface is closed so that it encloses a solid E, so imagine you have a surface that actually closes itself off. A sphere is a great example of a closed surface. The solid in which it encloses we call E. Then positive orientation of the surface is the orientation where the normal vectors point away from the solid. So back on that sphere, the reason why we called positive orientation was because this sphere encloses a ball, right, a solid ball. Positive orientation is where your normals point away from the solid. Negative orientation, they point in towards the solid. We good? All right, and we finally have gotten to a surface integral of a vector field over a surface. So now we're going to be looking at that surface that's been sitting there for the last 2 classes, and imagine that it's sitting inside of a vector field. That vector field might be magnetic, it might be gravity, it might be electric. I thought I said electric. I did? Magnetic, electric, okay. It could just be, some flowing material, whatever. But it's now a vector field. Instead of a scalar function, we have a vector field. We will define, if we're given a vector field on an oriented surface, S, with unit normal vector n. What's unit normal vector n? That was that cross product of the partials divided by its own length. And the vector equation of the surface, if we know it, then this integral, notice the formula here. It's a double integral over the surface S of the vector field dotted ds. So you're actually integrating with respect to, it's not surface area anymore. Do y'all see that? This is not d capital S anymore. It's d vector S. What the hell does vector S mean? I'd like to try and explain what it means in the formulas that you see here. Because this right here is the d capital S. I'd like to try and come up with some meaning for that for you. All right? Here's my best attempt at trying to explain what it is and what this whole thing called flux is. Okay, and I'm going to use an oriented surface. I'm going to use a sphere as an example. This is an infinitesimal little patch on the sphere, right? I'm going to move this thing. Come on. I've got to get this over here. At every point on this sphere, we have 2 vectors that we're looking at right now. So the point I'm looking at is this point right here. Man, those look like they're exactly the same. Let me get to the different points so you can see that these are different. Okay, there we go. I think that's a little better. So at this point, I have a green vector at that point, and I have a red vector. What do you think the red vector is? That's your normal vector, okay? That's your normal vector. It's oriented positively, so it's pointing outside of the solid, right? What do you think the green vector is?
It's the vector of the field.
That's the vector field vector, right? So remember, when you're in a vector field, at every point there's a vector, right? Has nothing to do with the sphere, right? So there you've got, at that point, the vector field vector, and you've got the red vector, which is your normal. What we'd like to do is, actually, you know what? The black, I should have said the black vector is your normal. I apologize. The black is your normal. The red, get the hell over here. I'm trying to get you to see what the red one is. Can you tell from that what the red one is? It's a projection. Okay, so I have to go back because I said the red one wrong. At that point, we have a normal vector. All right? And we have a vector field vector. If I do the projection of this green one onto this black one, I get the red vector, right? And what that red vector represents is, let's go back to water flowing, all right? If you're looking at that point, the water wants to flow in that direction, doesn't it? With a certain magnitude, a certain speed. If I project it onto here, this red vector tells me what the flow is in that direction. And the length of it is shortened now, right? Because it's been projected. So the flow in that direction is actually shorter than the flow in that direction. But all I'm interested in is the flow out of the surface. So that red vector represents that flow at that point. Does that make sense? So let's go back and look at this red patch. And let's imagine that we take a bunch of points. That's 4 points in that patch, right? Those are all normal vectors. Let me give you some more of them. There's a couple more. Those are all little normal vectors in that little patch. Let me show you all the vector field vectors that go with all of those. Okay, so those are all the green vectors that go with all those black normals. Let me project all those green ones onto those black ones, each one of them individually. And I get these red vectors. And I'm going to now take the normals and the vector field out. Those red vectors show you the flow out of that patch in the direction away from the surface, right? Like these things are running perpendicular to the surface. So this is somehow measuring how much is coming out of that patch. If it's magnetic field, electric field, gravity, whatever it is, it's a measurement of that flow, right? And if I add them all up, and I get a bunch and a bunch and a bunch and a bunch, right? Then I want to know like a measurement of all of this, right? And that's what flux is. It is a measurement of all these vectors coming out. Now, I'd like to go to the formula. I was trying to get us to see what this was, right? And I was saying that that was ds. So it's hard to, well, boy, you're really not going to be able to see it from here. Maybe you'll just have to trust me. Maybe next class I can put it up here for you. You have to go back to your projection formula. How do you project a vector onto another vector? There's a formula for it, right? If you come in here and you start putting your field with the normal vectors, things will start to cancel out, and this is what you're left with. So you have to believe that from this is actually your field projected onto your normal vectors. That's what that computation is. And then what you're doing is you're adding them up over the surface, if that makes sense. But when you project a vector onto a vector, don't you get a vector? Right? So this piece right here has to be a vector, which is why we say D capital S vector S. All right, I hope that kind of makes sense. All right, let's try and see if we can do one of these. Find the flux of the vector field capital F of x, y, z equals y, z, x across the unit sphere. So they want flux, right? So here's what I want. Double integral over S of the vector field dotted with ds, which is double integral, and go back to the formula. I only pointed out one of the two formulas. The one I'm going to use mostly in here to begin this is this one right here, okay? We will use that one sometimes. So F dotted with R, partial of R with respect to U, cross partial of R with respect to V, dA, and this will be over D. Okay, R is the function that draws the surface. We've done this. This is a unit sphere, right? So what was R? Yeah, okay, let's go. Was it sine U, cosine V? Sine U, sine V.